Welcome back. Today we will be looking at beam interactive design. So we're done with column. So it's now left for us to look at the beam and understand the results. Then we'll make our own judgment. All right. So let's look at this first beam. So just like the way we explain the column, you can see this is axis. This is the story is being found. This is the beam number. This is the quantity. And this is the pattern you're using for your design. This is your design status. So red means it's failed, good is okay. Then like I explained, this is the same thing as the utilization ratio. So it's the same thing the way I explained the column, like why it is here. And then this is the beam as well. Alright. Um so and take that as all. We have seen how this is done. Then if I select any of the beam, I can build the bending moment diagram and the shear force diagram. So we can understand how the beam reacts. Okay, so now this one to this place is where the plate beam ended. Plate beam started here and ended here, right? Then the first floor started here. So why I'm saying this because I'm not going to check anything under the plate beam because one thing I normally say is that a structural engineer or a structural designer is also a construction engineer. In the sense that before you be able to design a very safe and stable structure, you must be able to know how that building or that structure will be constructed. By knowing how it will be constructed, it means that how every element in that house, how those things are going to be supported. Your you're able to know how the slab. You already know how the slab is supported. You know how the blocks, partition walls, how are they supported. Everything about that building. You must know how it is being supported. And how will you be able to know that? By knowing how the construction is going to be. So from your head, you already visualize the construction process. And that is why you'll be able to design efficient and a what stable what building. So for this plane beam, it's normally at that ground floor level. So and one of the main purposes there is to change the columns, and because of that, when they are even constructing it on site, they will be resting those beams on the wall. So it's not like the beam is entirely suspended like the first floors and the second floors or the roof beam. They are not suspended entirely. Almost all part of it is going to what is going to rest on the block. So for that plane beam, 2y16 up and down is going to work. So what I normally do is I don't normally waste my time looking at the plane beam. Alright. So where I look at is the suspended beams, right? So we click this and let's see what we have. So as you select any of the beam, you click on extractive design and it will bring you to this place. So this is where you're going to take into. So this is a 3-span beam. These are the columns that is supporting it, right? Now, when you come here, this is under rebar. Now this rebar, you can find we have different patterns. What I mean by pattern is the way you arrange your reinforcement in a beam. That's what I mean by pattern. When you come to the Indians, mostly that I know, and other part of the world, they use what we call the bent up pattern. So it's a different way of arranging your reinforcement on the slab. So basically, what we use in Nigeria is pattern 2. Then If you are not a Nigerian, you can as well check up the pattern being used in your country. So that is why we are using pattern 2, and you can here come here and change the pattern. So when you come here, you want to view the bending moment diagram for this beam. So when you click, you can see the bending moment. These are the values. So the highest moment here is this. That is the hugging moment, while that of the sagging is this. So and this is the shear force. Okay, so this is where you look at the diagram. Then when you come to the detail drawings, you want to look at how the reinforcement will be, because these ones are just kind of scattered. They are not kind of they're kind of scattered. Like as you can see, it looks like a broken lines, right? So if you want to actually visualize how this will be, you click on detail drawings. So when you click on detail drawings, as you can see, these are the reinforcement. These are the reinforcement. These are how it will be placed. This is the reinforcement. This is for the links. This is for the links. This is this for the bottom reinforcement. This is for the support reinforcement. This is support. This is the span reinforcement. So you see that there is a lapping here of 50D. There is a lapping at this junction 50D. Okay. Likewise here as well. So this is the section. You want to look at how the section is. This is it. And you can see that the sections were cut here. The sections were cut there. So that is when you look at, you want to know how, what this reinforcement will look like. Then this is when you want to view the bending moment, the moments and all that. So I think that is all for this. Maybe if you want to generate reports. Then when you look at this one, you have beam. When you click beam, you can see the three beams we have, and from here you can change the depth and the width as well, and this will tell you the clear span. This is the span and the member. So then when you look at this, there's always we call the factor of safety in every design. Like you specified concrete grade of 25 megapascal, you don't expect them to use the 25 into the design, because it is very much assured that on site they might have something higher than 25, and at the same time they might have, after casting, when you check the compressive strength of that concrete, you might see that it will not be 25 as specified by the structural engineer. Sometimes it might be greater. So but because of those things that can occur based on the technicalities of the construction sector. So you see that Prota is specified 25 and Prota is using 16 to design. So he's assuming with a concrete grade of 16.67 to design this structure. You understand? So even if you specify 25 and they end up using 20, you see that the building still stands. That the building still stands. Likewise, we specified 410, but Puta is using 356. Even when they use 400, you see that it's still safe. All this needs to account for the errors of site and the material, uh, and the material, the way it's being manufactured. It's not, sometimes it's not much manufactured up to standard. So that is what this is showing you. All right. Now let's come back to the bar. So like when we click on this, when we look at the section, you see that we're having reinforcement up, reinforcement down. The space is the concrete cover. We enter 25. This is the links. So you have up and down, right? So when you now look at this, we have this value and this value up and down. For down, the reinforcement are down, for reinforcement up. And what is it telling you that after the analysis, the bending moment that was generated to solve so to solve the bending moment, this is the area of steel required. So for such the area of steel required to counter what the bending moment. So this is the area of steel required to counter such to counter the bending moment. So this for the top, this for bottom, top, bottom, bottom, bottom. Alright. So when you come here, so you discover that this provided two Y12. So and after the two Y12 attained up to this point, okay, let me use calculator to let's use calculator. So this is the extra area of steel. All right. Okay, let me just quickly explain this. Um, okay, for designs, for those of you, or I believe, for you to have registered for this course, I believe you must have gone through um, the manual design of reinforced concrete in your 400 level. If you went to Nigerian University, so I believe you must have done manual design. All right. So we have what we call the maximum area of steel required. We have the maximum area of steel. We have the required area of steel, and you have the minimum. So you see that the required area of steel must be within, or the area of steel provided must be within must be higher than minimum and less than the maximum. So for each of these span of the beam, this is the minimum, this is the minimum based on your beam section. This is based on your section. That's why it's crossed out, because the beam is 225 by 450, 225 by 450, 225 by 450. So that's why the values are what? Constant. This is the minimum at the bottom, minimum at the what? Top. That is for the area of steel that you provide for this beam must not be less than this. Must not be less than this. That's what this is saying. Alright. Now we have the S bar center line. I don't know what the CL is, and the bottom. So what it means that the spacing or the distance between two reinforcements, both top and bottom. What does this mean? If I click on this now, when you go to this section, it's not saying the from this center of this reinforcement to the center of this reinforcement is what we call what the software called the S bar, which is the distance between two reinforcements. When we have the top, we're talking about the bars at the top and down and bottom for the reinforcement at the what at the bottom. So that's why we have the top and the bottom. So what actually is the meaning of this? What information are we getting from this? So let's increase this bar diameter. As you can see, we are having this as red. Even when you print, when you click OK, your design will not fail. As you can see, it doesn't fail, even though this place is showing what? Red. And where this started to show red is when I started using 4Y16, so I increase it to 5. So as it's telling you that the spacing between the reinforcement at the bottom is less than what 19.8. Let's look at the detailed drawing. As you can see, so the distance between these two reinforcements is less than 19.8, and that. So the implication now is that your concrete, you are using a maximum um, size of aggregate should be what 20 mm. So and the spacing between these two is less than what 19.8. So how will you now, when you cast your concrete, when you pour your concrete, how will it be able to what pass? You see that the reinforcement will hang on the reinforcement. The aggregate will hang on the reinforcement, while the liquid aspect of the concrete will flow. This will now cause what we call the what segregation. So when such thing happens, and also there is no way your concrete poker or vibrator will pass through, because I think the size of concrete poker is 25 mm, and also the code specify that the spacing between two reinforcements should be what 20 plus 5 mm or 20 plus 6, which is a minimum of what 25 mm. The minimum should be between two this reinforcement is what 25 mm. So when you increase this now to this, you discover that they will have issue on site. They will have issue on site while pouring concrete. There's going to be a segregation. So you see that this is not right. So that what this top, bottom, the S bar and the S bar mean actually. So if you increase this one now, it will start showing red. Understand? Even though if you observe as well that this is less than 37, but it's showing red. This is based on the settings we made. Let me reduce it. So based on the default setting, the minimum spacing between two reinforcements is 50 mm. That is based on the software default setting, and that is why the 61 point something is not showing red. But once you are less than 50, once you are way less 50, it will show red. But even though it is showing red, it does not mean that they will have error on site, because this is 37, way greater than what 25. So this will not be issue on site. So even if you show red, you can go on and print it this way, because you already know that it is not, they won't have issue on site. Alright, that's what this actually means. Then when you come here, you see the deflection check. This is where you check if this beam fails in deflection, and you have the actual deflection and the allowable deflection. This 55.12 is the allowable what deflection, and the actual deflection of this beam is 10.09. So 10.09 is the actual, while the allowable is 55. So the actual should be less than what 55, and that is why this is not showing red. If you have a failure due to deflection, here will be red. So likewise for this ones as well. Okay, this is also the area of links supplied, the area of links supplied, right? And this is where you design for shear, which is your links. So this is the shear force, this is the concrete shear, this is the area of steel required, then this is the provided and all that. So when you click on this, you can increase it to make, if you want to use two leg of what reinforcement, you can actually do this and check the detailed drawing by yourself to see what you actually have. Okay, I don't think there's a session there for it, so you can do that on your own. Then this is when you want to increase the size of the links. It was y10, y8, and I clicked here, I increased it to y10. So if I click the down, I will reduce it to y what 8. Then the last one here, the maximum spacing is 300. That is why it stops at 300. But if you want to go down or if you want to reduce the spacing, you can click here. As you can see, it's already what reflected. So that is for that. Now we have the top reinforcement and we have the bottom reinforcement. So this is for the top bar. This is for the top bar. Observe if I increase the number of reinforcement, likewise this also what increases at the top. If you can observe, it's always increasing at the what at the top. Right. Then for this support here, this is for the support. Remember, this is support span support. So I can come here as well and input the support bar as well. As you can see, so if you view the detailed drawing, okay, you can't see that because it's on the same level or the same layer. So this is where we set the layers of your rebar. So this one is already layer 1. So if I want to make this one layer 2, I'll come here, click and select layer 2. If you want to make it layer 3, you come here and select layer 3. So we're making it layer 2. So what actually is this layer 1, layer 2? Let's see if the detailed drawing will show us. Complete the drawing should be able to show us what it means. So as you can see now, this is the bottom reinforcement. This the span reinforcement, that is the first one, the first layer goes all the way from here to this point. While for the bottom, which is only the support top bar, we go from here to here. Let's look at the section. Okay, so what the layer means is that this is for the first layer. So you know, in a case where you have like 5Y16, and you know that when you put the 5Y16 inside 225 mm size of beam, you're going to have spacing less than 19, which is a problem for casting. So you can decide to make two on a different layer. So this different layer means you want another set of bar to be arranged on top of this. So you see that the spacing between this one should not be less than what 25 mm. So if you make it a third layer, you still find another reinforcement at this part. Alright, so that's what they mean by what it means by these layers. This is what I mean by these layers. Alright. So but this one, like as you saw, as you can see from here, that this one extended all the way down to this place. Alright. So we now observe that without this support bar, this can handle the bending moment here, and that is why it is okay to leave this one. But let's assume that this is not sufficient enough to handle it. You can now introduce your support bar. So likewise, when you come here, you have your support bar 1, that is the first layer. Then as well, you can have support bar 2 in the second layer, just like what we did here. This is first, this is second layer. First for the support, this second layer for the support. Likewise, this one as well have first and second. Do you understand? So that is what this actually means. Then you come to the bottom. The bottom have the first layer as well, and they have the what? The second layer. Likewise here and here. Then this one means at the bottom. This one is for the support at the top. But at the bottom as well, you can still have a bottom bar for this one somewhere here. This will support at the bottom somewhere here, as you can see for. Then this is for the web bar. Let me add it. Okay, what does web bar mean? So let's view the detailed drawing and see what it means. So you see that this is the web bar. This is the web found at half of the beam depth to handle torsion. If your beam is subjected to torsion, you introduce a wheel bar to handle the twisting. Or if your beam, according to Eurocode, if your beam size depth is from 750 and above, so not Eurocode, Eurocode is 1000 and above, 1000 mm, which is 1 meter. While BS code is talking about 750. If your beam depth is up to 750 and above, we need to introduce a wheel bar to control cracks. All right. So when we view the detailed drawing, you can see it here. You can see it here. All right. So that is for this. All right. So how do you know when your beam is subjected to torsion? When you click one of these links, uh, if there is a torsion, it will come up here. It will show you the torsion. If it's Protastructure it will write here no torsion. But I believe this one will show if there's any of them subjected to torsion. That is when it will be written here. But I don't know why they removed it in this 2024. All right. So that is all about this. So from here you can now do your interactive design and decide yourself what you want based on your judgment as a structural engineer. Now, according to standards, Nigeria standard, um, I don't know if, but when for me, for me, when if for a floor beam, that is a beam that is supporting a floor slab, the minimum size of reinforcement I use is 16 mm. As far as is supporting what a floor. So the minimum reinforcement I use is Y16. Then I also use the minimum depth of what 450. I don't go below 450 for a beam supporting a floor. But when you talk about roof beam, I go with a minimum of what 300 and a minimum of what Y12 for roof beam. Okay. So because of that, you see this one, what can work for it is what Y2Y12. But because I don't want Y12 in my beam details for the floor beams, I will now increase it to what? Increase all of it to Y16. Okay, this one failed. Instead of providing another layer here, I can make it 4. So it's less than 31 and above 25 is still okay. Alright. So this is what I just wanted to do. And I'll say okay. Alright. So what we just did now was able to understand the what this interface is saying and what we can do about this. So it is now left for you or for us to go through these beams one after the other. We're going to go through them one after the other, even though it is showing good, it is marked good that it has been designed. So why we go through them one after the other is to make our own judgment. Because sometimes this software we use a reinforcement of 20 mm for your beam, but you discover that 4Y16 can actually do that, or even 3Y16 can do that most of the times. And that's why they say software is garbage in, garbage out. You are left to be the structural engineer you are meant to be. So we are going to go into those beams one after the other to make sure that what we are producing or what detail we are generating is based on what structural engineering what judgment. So like this one now, if you go into this, you see, because I don't want white work, I have to go through to see that everything is the way it is. I'll come here to make my judgment as well. Okay, so that's what we're going to be doing next. We're going to be going through these beams one after the other, and like as well design this one that failed. You want to know why it failed and what solution can we provide. Okay, see you in the next section.